My name is Ritesh Pandey, and in this class, this video, we'll continue our discussions on coordination compounds or complexes. Now, this happens to be class 2. In the first class, I get you started with terms like coordination number, ligands, the complex part of a salt, how they differ from a normal double salt. And in this class, we'll take up the reason behind the formation of these complexes, theories which explain the formation of these complexes. So right away, if we talk about a compound like K4FeCN6, you could see this, the enclosed portion would tell you that this is the complex part of the salt. It could be the anionic part of the salt, or it could be the cationic part of the salt, like in tetramine copper sulfate. And basically this portion would not ionize, this would not ionize. So this part, which is called the complex part or the coordination sphere, would have two components, a lone pair donor, which is say cyanide here, the ligand, and the lone pair acceptor, which is iron, generally a D block metal. Similarly here, the ligand is ammonia. Ammonia is the lone pair donor, copper is the lone pair acceptor. You remember everything outside the square bracket will ionize, it's called ionization sphere, this is called the coordination sphere. Now, with oxidation number, you balance the charges and you get cyanide -1, potassium +1, iron is in form +2 here. Similarly, this is -2, ammonia is 0, so copper is +2 here. The charges over copper and iron could well be obtained. This is ferrous, this is also cupric. But what goes into the formation of these complexes? And the first significant theory is the Warner's coordination theory. The first significant theory is the Warner's coordination theory, which was published in 1893. So this theory, which is given by a scientist Alfred Warner, I repeat, it's called coordination theory, and he proposed that every metal has two types of valencies. There is something called a primary valency, and then there is something called a secondary valency. So I repeat, the theory suggests, this man proposed, that every metal has two types of valencies. There is something called a primary valency, which we are more used to. So primary valency will be the number of electrons lost, which is the natural tendency of metals. Ferrous would mean 2 electrons gone, ferric would mean 3 electrons gone, cuprous 1 electron gone, cupric 2 electrons gone. So primary valency is the number of electrons lost by a metal, and secondary valency is, suppose, the number of lone pairs accepted. So the theory says that there are two natural tendencies of every metal. One, to lose certain number of electrons, which is the primary valency. This is more popularly called as the oxidation number now, and secondary valency is more popularly called as the coordination number now. So the rule is simple. Every time a metal exhibits only primary valency, it produces normal salt. So you could see ferrous here, and any other ferrous salt, suppose you have ferrous sulfate. Here again you have iron +2, here again you have iron +2. This is also ferrous, but it's a normal salt. Because only primary valency is exhibited, and in cases where both primary and secondary valency, both the valencies are exhibited, when it loses certain electrons, and then the natural tendency, the secondary valency, the second tendency to accept certain number of lone pairs is exhibited. When the metal exhibits both primary and secondary valency, it results in the formation of a complex or a coordination compound. In an example like K4FeCN6, naturally, I could say primary valency or oxidation number is +2, and secondary valency is the number of lone pairs taken, which is 6 out here. Another example which I had given you, CuNH3 4SO4, here naturally copper is again +2. So in a complex of this kind, I can say that primary valency is again plus 2 and secondary valency, which is number of lone pair accepted, this time again ammonia being monodentate, secondary valency here is 4. So this is a theory which explains the formation of these complexes. There was another scientist, a contemporary called Sidgwick. Now Sidgwick's theory might not be in your school scheme of things, it might not be in all the textbooks, but in all India entrance exams you'll have to learn Sidgwick's theory. And Sidgwick's theory, which is also called effective atomic number rule, Sidgwick's theory, which is also called effective atomic number rule, EAN rule, effective atomic number rule, it substantiated the concept of primary valency and secondary valency. Although you know atomic number happens to be the number of protons. Clinically, atomic number happens to be the number of protons, but here by atomic number we'll assume the number of electrons. So we'll not want to be very critical about the term atomic number. Here atomic number would stand for effective number of electrons around the central metal. And this man proposed that effective atomic number would be atomic number which is the number of electrons you have initially. Atomic number is the number of protons and you have the same number of electrons as well. Here by atomic number I would mean the number of electrons around the central metal. So how do you calculate effective atomic number? Effective atomic number will be calculated as atomic number minus primary valency, because this is the number of electrons gone, plus 2 would mean 2 electrons gone, plus 2 times the secondary valency, because this is the number of electrons taken up. Remember, this is the pair of electrons taken up. So this man said that if you calculate the effective atomic number, which is atomic number minus primary valency, the number of electrons lost, plus 2 times the electrons gained, effective atomic number would be equal to the inert gas configuration. So this is the reason why, in some cases a metal is going to exhibit, 2 types of valencies. I repeat, this effective atomic number rule is a part of all India syllabus. You might be given complexes to calculate the EAN. How do you calculate effective atomic number? It's supposed to be atomic number, which is number of electrons to begin with, minus the number of electrons lost in primary valency, plus 2 times secondary valency, which is the number of lone pairs accepted. So this is the total number of electrons around the central metal. And suppose if I find EAN for this particular complex, naturally iron is 26, atomic number is 26. So here effective atomic number would be 26 minus, the primary valency is 2 and the secondary valency is 6. So 26 minus 2 plus 2 into 6, and it would add up to 24 plus 12, which is 36. Now 36 is the atomic number of krypton. Helium, neon, argon, krypton. So this is inert gas configuration. We have learnt about inert gas configuration to be very stable. Magic numbers 2, 10, 18, 36, 54, 86. So this was one theory which was explaining why primary valency and secondary valency are exhibited, a reason behind the formation of these complexes. And we can take up more examples. In the sense, a very important complex is K2HgI4. You might well know this complex because it's Nessler's reagent. Alkaline K2HgI4 you would know is Nessler's reagent, a very important reagent to test ammonia and ammonium salts. Now here again, taking iodine -1, potassium +1, you would see it's mercuric. So here the primary valency is 2 and secondary valency is the number of lone pairs, which is 4 iodide. And how do I find the effective atomic number of mercury? Now this is where recalling all 3D, 4D, 5D will be important. In due course, We cannot make headway in due course. We cannot make headway in this topic if all of 3D, 4D, and 5D is not recalled. So time now to very quickly look at all the transition elements in periodic table. So the first series, which is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, is generally recalled. This is 3D. So most of you would be recalling 3D. Now 4D is yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium, and as I told you, not only for this topic, for inorganic chemistry, periodic table, D block, the chapter D block, at some point of time you will want to recall 5D, lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury, along with their configurations and atomic numbers. So the fact that copper, silver, gold are in the same group, they were called coinage metals. Zinc, cadmium, mercury are volatile metals having complete D10, are things which you remember. Iron, cobalt, nickel, ruthenium, rhodium, palladium, these were the triads in the old periodic table. But trust me, at some point of time, knowing palladium, platinum are below nickel would be very, very important. You'll have to remember palladium, platinum has the same configuration as nickel, which is D8, 3D8, 4D8, 5D8. Some mnemonics are very popular among the student fraternity. So although the first one is known, second one, third one, I've learned some mnemonics from some students. So again, this is very popular. You would have heard like a mnemonic, La hafta varna udar idhar pitai aur hogi. La hafta varna udhar idhar pitai aur hogi is a way to recall lanthanum, hafnium, tantalum, tungsten, rhenium. Udhar idhar pitai aur hogi is osmium, iridium, platinum, gold, mercury. So naturally it's your choice. You learn it by a mnemonic or you learn it by your own. Such mnemonics for 3D, 4D, 5D are very popular, as I told you. You might well find it in YouTube channels, or your friends might tell you. But some way or the other, you'll have to remember all of 3D, 4D, 5D along with the atomic numbers. So this is following, or this is preceded by calcium. So calcium was 20, this is 21 to 30. This is 21 to 30. The difference is 18. The difference is 18. So no, this will be 48. This will be 39. 21 to 30 is 3D. 39 to 48 is 4D. You add 18 here, you will have 57. Then you might remember 58 to 71 would go to 4F. Here again you will want to resume from 72. And the difference will become 32. 72 to 80. 72 to 80. The difference will now become 32 because 14 would have gone to the F orbitals. And this is where remembering mercury 80, gold 79, platinum 78 would help not only in finding the effective atomic number but also in the due course. So if you go about finding the effective atomic number for mercury now. So now mercury is 80, mercury is 80, so EAN here could be calculated like atomic number is 80 minus primary valency, which is 2, plus 2 times the secondary valency, which is 4, and 80 minus 2 plus 2 into 4, 80 minus 2 plus 2 into 4 naturally would be 78 plus 8, which is 86. Now 86 is for radon. 86 is for radon. Somewhere here, helium, neon, argon, krypton, xenon, radon. So this is 36, this is 54, this is 86. 86 is for radon. So this is going to work for so many complexes. This is going to work for so many complexes. I told you this theory will have a period of glory, and there are questions from this topic. It explains the formation of complexes. The idea is, by losing some electrons in primary valency and gaining some electrons or lone pairs by secondary valency, it's trying to achieve or arrive at inert gas configuration. A very popular example is K2PtCl6. K2PtCl6. So now platinum is 78. and minus 1 plus 1 would tell you minus 6 plus 2 minus 4. Platinum is here 4, and naturally secondary valence is 6 lone pairs, ligand 6, it's 6. So you'll want to start with 78. You'll want to start with 78. Effective atomic number you know is atomic number minus primary valency, which is 4, plus 2 times secondary valency, which is 6. So yet again I think 74 plus 12, 74 plus 12 would again give you 86, which is the configuration of radon. So for so many complexes this theory is going to work. For so many complexes this theory is going to work. And whether it's about calculating the effective atomic number or in the long run, I told you all of 3D, 4D, 5D needs to be on your fingertips. Even from the days of periodic table, atomic structure, you're supposed to know that zirconium, hafnium, are in the same group, lanthanide contraction, which is because of 4F, they're called lanthanides. You will find zirconium and hafnium would have comparable radii, they'll be almost of the same size. So even in the past, you would want to recall members of 4D, 5D. High time, all the members of 3D, 4D, 5D along with their configurations and atomic number. It will help in the sense iron 26 will be 3D6, 27 cobalt will be 3D7, 4s2, and so and so. I told you platinum below nickel is something you'll want to know for sure. Some of the earliest known complexes were the carbonyls. Some of the earliest known complexes were the carbonyls, and three popular carbonyls which were very early discovered were carbonyls of nickel, iron and chromium. So suppose these are three carbonyls, we write away because carbonyl will have a charge 0. The primary valency of all these complexes would be 0. So for these three carbonyls, I would write that the primary valency is 0. And secondary valency, naturally, if the formula is NiCOX and FeCOy and CrCOZ, secondary valency would naturally be X, Y and Z. And when the formula of these carbonyls were known, and it was found that the value of X, Y and Z are 4, 5 and 6 respectively, and the corresponding EAN calculated, this would again obey the Sedgwick's theory in the sense, nickel is 28, so this will be like 28 minus 0 plus 2 times 4, iron is 26 minus 0 plus 2 times 5, and chromium would be 24 minus 0 plus 2 times 6. So I repeat, when these formulae were known, this was tetracarbonyl, this was pentacarbonyl, and this was hexacarbonyl. When these formulae were known, naturally 28 plus 8 and 26 plus 10 and 24 plus 12, they'll all be equal to 36, which I've already told you is an inert gas electronic configuration or number. So for a while, so many complexes were supporting effective atomic number rule, and as I told you, this theory had a period of glory. We'll want to learn how to calculate the effective atomic number. So far I've given you cases which have obeyed effective atomic number. Time to talk about the variations. When a few more complexes were discovered, so realize it all began with the example K4FeCN6, where I was happy finding iron 26 minus 0 plus 2 into 6, minus 2, I'm sorry, it's ferrous. It's ferrocyanide, it's Fe plus 2, minus 1 plus 1 would prove it. So 26 minus 2, 24 plus 12 was 36, we're happy with this. When a complex like K3FeCN6 was discovered, potassium ferricyanide. Now naturally ferricyanide will be Fe plus 3. And with Fe plus 3, primary valency being 3, effective atomic number will be 26 minus 3 plus 2 into 6, and this will fall short by 1. So instead of 36, it's 35. Instead of 36, it's 35. It's not krypton configuration. It's not inert gas configuration. In ferricyanide, the effective atomic number rule is failing. Now, when more such complexes were discovered, where the effective atomic number was not equal to inert gas configuration, the argument was that, all right, even if it's not touching 36, it's trying to reach 36. I repeat, with more and more complexes, known and discovered where effective atomic number rule was not obeyed, like in this one, it's not 36, it's 35. The argument was, although it's not reaching 36, although it's not equal to 36, it's trying to reach 36, it's trying to become inert gas configuration. And the major blow came when it was realized that one which is trying to reach inert gas configuration is actually more stable. Ferricyanide was found to be more stable. So when ferricyanide was found to be more stable, naturally, over ferrocyanide, which is less stable, I'm talking about the relative stability of these two. When ferricyanide was found to be more stable than ferrocyanide, it's like when 35, which is not an inert gas number, when it's trying to reach inert gas configuration, when this was found to be more stable than the one where it's already 36, you know that time to learn better theory. It's not only a number game, but again, because for so many complexes this theory is working and it's very much in our syllabus, we'll want to learn everything about effective atomic number, but now we see a drawback of it. In the sense where it's not becoming 36, it's becoming more stable. Now, naturally, when I look at these two complexes, ferrocyanide and ferricyanide, knowing nothing about effective atomic number, knowing nothing about primary valency and secondary valency, to any observer, or a basic understanding would tell me that ferric will attract cyanide more than ferrous. Ferric will attract more than ferrous. Charge plus 3 will attract negative dipole more effectively than charge plus 2. Ferric more than ferrous, cupric more than cuprous. Higher the charge, more positive charge. Naturally, the metal will attract more effectively. It will bind the ligand strongly. So, as I told you, this is basic physics. Ferric will attract more than ferrous, and naturally, ferric had to be more stable than a ferrous complex. And the rule will be, for the same pair of metal and ligand, certainly one where metal is in higher oxidation state, I repeat, for the same pair of metal and ligand, one where metal is in higher oxidation state will produce a more stable complex. So, ferric will produce more stable complexes than ferrous, cupric will give you more stable complexes than cuprous. The number game is going to fail sooner than later. I told you a few cases where it was working, there will be a few cases where it will not work. What comes to my mind is C1H4SO4. Even in tetramine copper sulfate, which is a fairly stable complex, a very important reagent in silk industry, it's a test of copper, a blue colored solution. Now, primary valency is plus 2, secondary valency is 4. So, with copper known 29 as the atomic number, 29 minus 2, which is primary valency is 2. This is minus 2, this is 0 naturally. Cupric. So, minus primary valency plus the coordination number is 4, 2 times 4, 2 times the secondary valency. Now, this will be 27 plus 8, which is 35 again. So, many more complexes were discovered where effective atomic number rule was not working, and naturally this was indicating or suggesting that we need to go back to the original concept, the original approach of overlap of orbitals, hybridization, and in the next video we'll take up the valence bond theory and hybridization, which basically would be involving orbitals, hybridization, and would explain the structure of the complex, the magnetic behavior of the complex, and more properties of the complex more effectively. So, this much for the time being. In the next video, we are going to talk about the structure using the concept of orbitals and hybridization. This much for the time being. Thank you so much.